Okay, so from the previous video, you might have this impression that memory consistency model is a contract. The hardware designer writes the contract, the software programmer will know what to expect from the machine. So I can come up with any contract. One of them, the most relaxed model would be to say, don't expect any ordering. Okay? I don't guarantee any ordering. If you want any ordering, put some memory barrier or such thing. That's the end of the story. Or you think. There's a catch. The catch is this. Even though that's right in general, specifically there is a, if you can call it an exception, that you have to pay attention to. That is, if you have writes to the same location, they are uniquely ordered globally among all the threads. What that means is you cannot say, well, there's no ordering. Writes to the same locations have to be globally preserved in some order that we can argue about. Now, writes to different locations, remember, they can be in different order. Even atomicity, we can give you that. We can review the fact that writes are not even atomic. So they're overlapping orders. You can't even tell if there is an ordering because there's two processes going on. But those are two different locations. Okay? But when the writes are to the same locations, somehow this is no longer a freedom that you can practice. You just have to write it up in your in your consistency model. Now, this is part of the domain of cache coherence. The fact that you're writing to the same location, this is the domain of cache coherence, no longer memory consistency. Doesn't matter what memory consistency model you provide, so long as you claim your system to be cache coherent, you have to do this, which is write to the same locations have to be globally ordered. We'll see what that means, but then this really completes the definition of cache coherence. And again, to me, I still fail to find why write serialization is so important, although I get it's nice to have a stronger model, a more limited model that we can reason about program behavior. I like that. But write serialization somehow is determined to be so essential, it's part of coherence. So really, write cache coherence is composed of two things. One is write propagation. This really says, okay, a write will eventually be globally visible. So if your system caches allow data to be cached, some write happens on one processor. At some point, doesn't matter when, at some point, this information is propagated throughout the entire system. Okay, but then when? Well, remember about timing. That is the matter of the consistency model. It depends. It depends on what the consistency model is. For relaxed consistency models, you may have a memory barrier. Then all you got to do is before the memory barrier is allowed to be passed, this write has to be propagated to everything. But in addition to write propagation, there is write serialization. Okay, if your system doesn't support write serialization, which is this thing that we just mentioned, it's not cache coherent. So that's the definition. And you have to pay attention to the fact that same location doesn't mean same word. It's not a word that's the unit here. Location, in my opinion, is purposefully kept vague. So there's more leeway to claim whether you are cache coherent or not. Again, the history is murky. I cannot trace back to who made the decision, what committee decided that this is the definition of coherence, but that's what's in the textbook, what's being taught and being discussed in these papers, if you trace long enough back to the chain. So what does this all mean? Well, let's perhaps look at my favorite example again. Remember this case? Look at the upper part of the slide where we have three processors running these three threads. We have this implicit assumption that the A equal to 1 is releasing P2, releasing the spin loop of P2, which allows B equal 1 to happen, which then allows P3's while loop to terminate, and then print A. So our implicit assumption is that if I run a code like this, assuming A starts with 0, we're not supposed to see A being printed as 0 in P3. But we also knew that because of this non-atomicity, okay, the fact that A equal to 1 is a right, that it is not atomic, means it can overlap with that of B equal to 1. So in this example here, there is no notion that A equal to 1 has to happen before B equal to 1. It does for as far as P2 is concerned. That's why you release, this is guaranteed by this, right? A has to be 1 from the perspective P2 for the second statement to even start. So from P2's perspective, no question, A happens first, B happens later. But from P3's perspective, if I have a non-right atomicity system, a non-right atomic system, then P3 can disagree and believe B equal to 1 happens before A equal to 1. And that's breaking, quote, the intuition. Okay? So that's the idea. That's what is actually allowed by alpha's consistency model. You run this piece of code, you run it multiple times, you may see A being 0 on some machine. So what's right serialization? If we look at the code later, okay, this is a slight adjustment of the previous code. We're no longer using A and B, two separate variables. We're using A, and the trigger of A equal to 1 will release P2's spin loop, and that will go on and set A equal to 2. So let's say this happens, and then when we see a code that is being released, a loop that is being released by A equal to 2, and let's say after some time, will we again see A reverting back to 1? Because there are two rights here, A equal to 1, that right, and that right. There are two rights. Okay. If we carry the logic from above, P2 sees those two rights in the same order, in the following order, 1 update to 1 being first, update to 2 being second. So this happens first, this happens next. According to the previous logic, then we may say here, maybe we see this, or this happens first, and this happens next, right? It's not right atomic. Rights do not have global order, so they get out of order. And when I print A, I would expect A possibly to be 1, right? No. The answer is now you're going to the same location, and there, to the same location, all memory accesses, all writes to that memory location have to be globally ordered. Therefore, this cannot happen. That A update to 2 happens before update to 1. This is not allowed. And so that's right serialization. If you have the most relaxed memory consistency model, you're still expecting the machine to always print out a equal to 2. It's impossible to be 1. Okay, if you print out a equal to 1, okay, your machine is not even cache coherent. So that's the difference between the two. Now, to show you what I mentioned slightly earlier, that it's to the same location, I want to highlight this litmus test, which is actually found in Alpha's architecture book. First of all, they have a lot of litmus tests. They cannot explain this in some grand theory alone. They have to show you case by case. Okay, remember this particular example, here's the case. In this case, this is possible, that's not possible, and so on and so forth. This is a little bit convoluted, the way they described it. So let's try to unpack it. What this really says is X is a memory location, and it's a quad word location. Okay, it's called X. Okay, it's a memory location, and it's initially this value, and that's in hexadecimal. So if you look at it, this is that's 8 hexadecimal digit. So that's 32-bit right there. So essentially you can draw it like this. Okay, so you have a 4-byte or 32-bit quad, maybe it's not a quad word, a word or double word. This entire location is called X. It has a lower part, has a content of 1, and has a higher part, which has a content of 1. So if you read the entire, let me see if I can show this view. If you read the entire word, then it's this value 1001, 1000, lot of 01 in hexadecimal. Okay, so that's the memory location. Now we're looking at 2 threads. Let's change back to red. So we have 2 threads, PI over here, PJ over there. Okay, the first instruction is a store or a write, but it's a write of 4, with 4 or 4 bytes. So it's not writing the entire thing. It's writing, let's say this is the way that I wrote it. Okay, so this is upper. So this is really, let's call this X. This would be X plus 4, its memory location. Okay, it's 4 byte later. And the whole thing forms an 8 byte or 64-bit word. Initially, it's this 100000001. Now, PI is going to do a write of value 2, but it's 2 memory location X. So it's going to update this from a 1 to a 2. If I can try this. Okay, we're going to update this to 2. All right. So what happens on the other side, PJ? It's pretty much the same thing, except it's updating the upper double word, the upper 32-bit. Okay, so what does this do? This will update this to 2. And then both sides will issue a read of width 8, the entire quad word. So they're going to read out the entire thing. So it's going to be one of these possibilities. They're initially 1. Later on, okay, they're initially both quad word are 1, and some of them are updated to, one of it is updated to 2, and the other updated to 2 at a different time. So you can, in theory, think about the possibility of these 4 cases. Okay, right? That's the only possibility. So the outcome is such that one thread returns 1, 2. Yeah, this is okay. You know what? Let me let me change this a little bit so we don't get confused. The way this is written, the higher order bit is there, so I'm just gonna redraw this. So we're gonna call this x plus 4, right? Initially, it's going to be 1, 1. So our logic would go, okay, one of these two, let's call this u1. So if it's u1, v1, if the order is u1, v1, we'd expect the memory location to go from 1, 1, and if u1 happens, x would be updated first. So that's u1, and then v1, right? We would expect the memory to go through this process. And if it's v1 happening first, followed by u1, we expect the memory location to go through this change. Okay? Oh, sorry. This is 1. So if you look at this, you will see in either case, one of them will print out a 2, 2. Because if this is the case, if u1, v1 is the case, v2 would happen after v1. It would therefore read the value 2, 2. If it's v1, u1, u2 will happen after both, and it will read the value 2, 2. Right? That's your intuition. But that's not the case. This piece of this litmus test says, look, this guy is going to read 1, 2 on the left hand side, 1, 2. Here it's going to read a 2, 1. Nobody's printing out a 2, 2. Okay? And this is possible. And so this goes back to the memory consistency model. I have two writes, one over here, one over here. There is no ordering. Nobody says it's either this order or that order. It's both. Both these orders happen. And if you follow their logic, it's written down here. It's a different way of thinking about it. So U2 is reading 1, therefore not V1's update. So U2 is happening before that. Similarly, V2 is reading a 1 on the lower word, so therefore it must happen before U1. Okay, and if you look at U2, it's reading U1 is visible to U2, so you'd think, okay, then there's an ordering. U1 happens before U2, V1 happens before V2. Then you would have an ordering. You would have an ordering circle. That's the circle. So which one is first? But if you read carefully, it says, well, these U1 and U2, even though U2 is visible to U1, but they're issued by the same processor. And so therefore this doesn't necessarily happen. Similarly, this doesn't necessarily happen. So I don't have an ordering. I don't have an ordering cycle. I mean, this is very confusing, right? U1 is visible to U2, but because they're issued by the same processor, therefore there is no ordering. What this really says is, I think a better way to say it is that in this processor, U1 is ordered before U2. But it doesn't mean in another processor it is. So I don't have this global circling order cycle because there is no global order. For PJ, that didn't happen. For PJ, U1 doesn't happen before U2. Okay, so this is to the same quad word. These two axes are all to the same quad word, but it doesn't matter. It's not the same location. That's what we mean. Even though it's to the same quad word, but it's different portion of it. Therefore, they're not to the same location. I've never seen any definition about what is a location. What about if they overlap? So it's maybe not purposefully kept vague, but it was never articulated in one place that is clear to me at least. So that's the thing we have to deal with. So the result is that for consistency, it's about ordering of memory location, memory accesses, what can be reordered, what has to be preserved, and an independent thing about a binary decision of whether you have write atomicity or not. We've seen that before. So if we flip back to the slide over here, we see on the left hand side we have all the memory consistency models that are write atomic. On the right hand side, these two are not write atomic. Okay, so that's memory consistency. Sorry about that. And this ordering has one exception, that is writes to the same memory location have to be globally ordered, and that's called write serialization. And coherence that's the domain of coherence. Okay, so consistency is about everything else, right? Not to the same location, and they have their different order. Sequential consistency being the easiest to understand, perhaps, but it's thought to limit implementation flexibility. And we'll see actually that's not the case. It actually gives us a lot of flexibility if we use speculative technique. So we'll see about that. But if I have an explicitly relaxed memory model, memory consistency model, then I can do a lot what I want in terms of optimization. So with that, we're going to go see the actual implementation. With that in mind, consistency model has a non-trivial impact on how we implement things. And we'll go next about how this is implemented.